counts. This is my third time trying to do this, so hopefully it'll be the one that works. I'm going to go over how to graph tangent, cotangent, secant, and cosecant functions by hand. And in class, in small groups, you guys worked out how to come up with the basic tangent function. So let's just talk about what results you got. When you found out that the tangent of x was undefined, you found out that those happened at some specific points, like x equals negative pi over 2, pi over 2, and you could have done it generically as x equals pi over 2 plus pi n, n an element of the integer set. And then you found out when the tangent of x was equal to 0, and you found that to be x equals 0, pi, dot, 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 and we could write it generically as x equals pi n, n an element of the integer set. Now certain things happen on the graph of tangent when you have a location that's undefined, and that is going to be a vertical asymptote. And so our vertical asymptotes for the first period of tangent that we're going to draw is that they're going to be a pi over 2 and negative pi over 2. And so I'm going to use a different color here to try to be creative without my whiteboard. I'm going to use blue, and so there we go. There is my first vertical tangent, my second vertical tangent. And then on the graph for tangent equals 0, that's going to be the 0 of the function. And so we're going to have a 0 at x equals 0. And if we were to continue our graph out here, we would have another vertical asymptote at 3 pi over 2. So I'll draw that really quickly. And then we'd have another 0 at pi, which would be right here in the middle. And then I asked you guys to plot or to figure out what some other points were. So what happens at pi over 4 and negative pi over 4? Well, the tangent at negative pi over 4, as you guys are well aware, is equal to negative 1, and the tangent of pi over 4 is 1. And so we are going to graph and connect the dots here. So that's one period of the tangent function, and it's going to repeat itself at 3 pi over 4. The tangent is negative 1, and at 5 pi over 4, the tangent is 1, and there's the second period of that. I should have gone through that point. Okay, now the tangent, unlike sine and cosine, the period is defined as pi over b instead of 2 pi over b, which you're used to. Another way, and this is the way I prefer to figure out what the period is to note the distance between the asymptotes. The distance between the asymptotes will also be the period, because that's what it takes to complete one full cycle. The period here is going to be the distance between pi over 2 and negative pi over 2, which turns out to be pi, because the b in our equation up here for tangent is 1. All right, so let's look at this graph, and what are the properties that we know that we can see? Like first, the domain. The domain for the tangent function is going to be all real numbers not equal to, well, where the asymptotes are. And we'll just choose one, and I'll choose the one on the left. That's negative pi over 2 plus pi n, n an element of the integer set. And then the range is going to be all real numbers. All right. Some other things that we can state about tangent are some facts about its continuity and its increasing and decreasing behavior and behavior limits. The tangent function is continuous. You might say, wait, Mrs. Muller, it's not continuous, but it's continuous everywhere except, and there's my exception, at x equals pi over 2 plus pi n, and an element of the integer set, because that is where we have infinite discontinuities. Can I spell? Well, you guys know me well enough by now that spelling is not my strong suit. Discontinuities. All right, so we know that it's continuous everywhere except at x equals pi over 2 plus pi n and an element of the integer set. Now, the other thing we know is that tangent of x is increasing. And we can do this with interval notation, and we can say it's increasing for all reals not equal to pi over 2 plus pi n and an element of the integer set. Or you could say this interval, negative pi over 2 plus pi n and an element of the integer set, comma, from pi over 2 to pi over 2 plus pi n and an element of the integer set. So we can say that it's increasing over those intervals. Let's do end behavior limits. That would be the limit as x goes to infinity of tangent of x, and the limit as x goes to negative infinity of tangent of x. And we can say that these limits do not exist because tangent is periodic, and it doesn't zoom in on a specific number. At positive infinity, it's still going to be repeating itself all the way, so that it doesn't zoom in on a number, so the end behavior limits do not exist. All right, what about the limits near the vertical asymptotes? We can say that the limit as x approaches, let's use this pi over 2 asymptote here. So I can say pi over 2 from the negative or the left side of tangent of x is equal to positive infinity, because as I get closer and closer to pi over 2 from the left, the y is going to get closer and closer to infinity. The other asymptote is going to be the limit as x approaches pi over 2 from the positive side, and that's going to equal, from the positive side, as x gets closer and closer to pi over 2, then this asymptote is going to get closer and closer to, or this function is getting closer and closer to negative infinity. Now, I can extend that to all of the asymptotes if I add this language in the limit language down here, plus pi n and an element of the integer set, and then plus pi n and an element of the integer set. And I've covered all of the vertical asymptotes when I have that description. Now, another interesting thing about tangent, the function, is there are no extrema. Now, what do I mean by extrema? That means no maxes or mins. Sorry, this is all over the page, but this is what I had to work with. And then this function is not bounded. That means the y's are not restricted from above and below. So this function is not bounded. And then the last thing I want to discuss about tangent is its symmetry. Now, we learned in our last identities unit that when we had f of negative x equals tangent of negative x, that tangent was an odd function. So when you do that, let me erase this, you can factor out, or you can take the negative out of the tangent argument, angle argument, and then we know that is equal to negative f of x, which means if f of negative x equals negative f of x, we know that it's odd, and it has symmetry with respect to the origin. All right, that's a pretty detailed description on the basic tangent function. So now let's move on to the cotangent function, which I have down here below. Hopefully we'll have enough space for that, but we'll see here. All right, so the cotangent function, when you were doing your discovery, I hope you realized that the cotangent of x is undefined at two different locations. That's going to be when x is equal to 0 and pi, dot, dot, dot. And generically, that would be x equals pi n, an element of the integer set. And that the cotangent of x was equal to 0 when x is equal to negative pi over 2, and so on. And so that would be generically pi over 2 plus pi n, an element of the integer set. All right? So now let's graph our cotangent graph based on this information. So similarly, we know that the cotangent graph, if it's undefined, is going to have asymptotes where it's undefined. In this case, it's going to be at x equals 0. So let me draw my asymptotes at 0 and at pi. And let's go to negative pi. So we're going to have asymptotes at any version of pi that we see, and at 0, and at pi here. And our function zeros are going to be at pi over 2. So at negative pi over 2 and pi over 2. And so we can put our zeros on the graph there. And now let's plot a couple of points. Well, at pi over 4, the cotangent is going to be the same as the tangent, and it's going to be 1. At 3 pi over 4, the cotangent is going to be in the second quadrant, right, and isn't negative 1. So we put that dot there. And then we connect the dots here for the cotangent graph. And instead of an increasing function, we have a decreasing function, and the same thing would happen over here. Not like my whiteboard where I can undo, so we'll have to bear with my graphs this way. All right, so let's figure out what some of the properties are for cotangent then. The domain is going to be all real numbers not equal to pi n, an element of the integer set, because that's where the asymptotes are every pi. The range is going to be negative infinity to infinity, just like the tangent above. This function is also continuous everywhere except at x equals pi n, and an element of the integer set where the asymptotes are, where there are infinite discontinuities. Cotangent of x, unlike the tangent, is decreasing for all reals not equal to pi n, and an element of the integer set. The n behavior limits. The limit as x goes to positive infinity of cotangent of x, and the limit as x goes to negative infinity of cotangent of x. Both of these, just like tangent, do not exist because this is a periodic function that does not zoom in on any n behavior number, which is nice that they don't exist. All right, I'm going to go up here and put the vertical asymptote limits. We can say that the limit then, as x approaches, and let's choose 0. from the left-hand side plus every pi n after that from the left side. So as x gets closer and closer to 0, the function is going to negative infinity. So we can say limit as x approaches 0 from the left side, or the negative side of cotangent x, is negative infinity. And the limit as x approaches 0 from the positive side of cotangent of x is equal to positive infinity, and we can put plus pi n and an element of the integers, and that covers all the asymptotes. So as x gets closer and closer to 0, from the positive side, the y is getting closer and closer to infinity. All right. The period is just like tangent. It's the distance between the asymptotes, and that's just, in this case, again, pi. There are still no extrema, so let's write no extrema, which means no maxes and mins. This function is also, I'm running out of space here, not bounded. That means the y's are not bounded from above and below. And the symmetry here is just like tangent. If I go f of negative x, meaning cotangent of negative x, from our identity unit, we knew that cotangent was odd, so you can pull this out. And we can say then this is equal to cotangent, negative cotangent of, negative f of x. And so we get f of negative x equals negative f of x, and we know that it is odd, symmetric with respect to the origin, and that is the basic cotangent function. All right, so let's move on and figure out how we can graph these when they're not just the basic functions, but we have some phase shifts and amplitudes and some vertical shifts. So I'm turning the page over in our notes here, and so the way that I graph tangent and cotangent is to, first of all, find the asymptotes, because if you know where the asymptotes are, you know the period, and since tangent and cotangent are both very symmetrical, then you can draw the rest of it very easily. All right, so what I do is I take the angle argument here, which is going to be b times x minus c, and I set it equal to where the tangent function is undefined. Well, the tangent function is undefined as we discussed earlier, as at x equals negative pi over 2 and pi over 2, and every pi n after that. But I'd like to just get two of the asymptotes, because once I know where two asymptotes are, I can pretty much predict where all the rest are. So we're going to set this angle argument to find the asymptotes. We're going to set the b times x minus c equal to negative pi over 2, and we're going to set the b times x minus c equal to positive pi over 2. And then we're going to solve for x. And when you solve for x, then that's going to be x equals the asymptote, which is really cool. And cotangent, like tangent, has an angle argument, and I like to find the asymptotes for it too. So let's find the asymptotes for cotangent by just figuring out where the cotangent of x is undefined. Well, you guys found out that the cotangent is undefined when x equals 0 and pi. Now those are just two of them, but when graphing we only need, as I mentioned, the two asymptotes to get started. So we're going to set our angle argument, which is b times x minus c equal to 0, and b times x minus c equal to pi, and then we're going to solve for for x, and then that will give us x equals the asymptotes. And then we can graph the rest of it from there. So let me start to find the asymptotes. So I always find the asymptotes first and then draw the rest of the graph after that. All right, so let's do an example here really quickly. And the first one I'm going to do is the tangent of x over 3. We're going to graph this. So step 1 is to find the asymptotes. So finding the asymptotes. What are we going to do? We're going to set our angle argument, which is x over 3, equal to negative pi over 2, and we're going to set it equal to pi over 2 because that is where the tangent is undefined. And now I'm going to multiply both sides by 3, and I get x equals negative 3 pi over 2, and I get x equals 3 pi over 2. So that's where my asymptotes are going to be. So I'm going to draw the beginning of my tangent function, and I know that my asymptotes are going to be at 3 pi over 2 and negative 3 pi over 2. And I'm going to draw my asymptotes now. Here we go. My baby blue color. All right, and now I know since tangent is so symmetrical that in the middle between my two asymptotes will be the midpoint point, or in this case, since I have no vertical shift here, it'll be at the origin. And halfway between these 2 points will be where the tangent is equal to 1. So I'm going to put a 1 here and a negative 1 here. All right, so halfway between 0 and 3 pi over 2, the calculation would be 3 pi over 2 plus 0 times 1/2. That's, I'm going to average, and that's going to be 3 pi over 4. So I know that this point is going to be 3 pi over 4, and that's going to be up at 1. And then since we have nice symmetry here, this will be negative 3 pi over 4, and I'll be at negative 1. And then I can graph my tangent graph. There it is. And that's one period of it. And the period, like I said, is going to be the distance between the asymptotes here. That's the period. Now how do we figure that out? Well, it's going to be 3 pi over 2 minus a minus 3 pi over 2. So we can say the period here is equal to 3 pi over 2 minus the second point, the end point over here. So you take the end point here, 3 pi over 2, or the asymptote here, and then subtract the previous one. And so we get 3 pi over 2 minus a minus 3 pi over 2 gives us a 6 pi over 2, which is equal to 3 pi. So the period is 3 pi. Now, that's the distance between the asymptotes, but I told you that you could find the period as pi over b. And b in this case is equal to 1/3. So we could say the period is pi over 1/3, or 3 pi. So there's a way to check your work there, which is kind of neat. All right, so what is the domain of this function? Well, it's all reals not equal to, well, you just choose an asymptote, and I'll choose the left one, negative 3 pi over 2 plus, how far apart are the asymptotes here? They go from negative 3 pi over 2 to 3 pi over 2, so it's going to be every 3 pi n after that, and an element of the integer set. And then the range is negative infinity to infinity. So that's pretty cool. There's our first tangent graph. And the x over 3 made it wider. All right, moving right along. Let's try a cotangent graph. My kitchen table. It's like a trig at home with a nice warm and fuzzy feeling, right? All right, so now we're going to do cotangent of, or 2 cotangent of 2x minus pi over 2, which looks like it's got a phase shift and it's got an amplitude but no vertical shift. All right, so step 1 is we're going to find the asymptotes by setting the angle argument So finding the asymptotes. We're going to set the angle argument, which is 2x minus pi over 2. And this is a cotangent function, so we're going to set this equal to where the cotangent is undefined. And that's undefined at 0. And 2x minus pi over 2 is equal to pi. So we've got 2x minus pi over 2 equals 0, and 2x minus pi over 2 equals pi. And now we're going to solve for x. So this is 2x equals pi over 2. And then I'm going to multiply this equation, both sides, by 1/2, and I get x equals pi over 4. And then this side, we get 2x equals pi plus pi over 2. And that's going to be 2 pi over 2 plus pi over 2 is 3 pi over 2. So we get 2x equals 3 pi over 2. Multiply both sides of the equation by 1/2. I get x equals 3 pi over 4. So now I know where both my asymptotes are going to be. And let's draw the graph. So there we go. There's my y-axis here. And here's my x-axis. And I'm going to put my first asymptote at pi over 4, my second asymptote at 3 pi over 4, and draw my asymptote in the nice blue color. All right. Now, like I said, cotangent is very symmetrical, and so in the middle, I'm going to have my x-intercept because I don't have a vertical shift up here. And this is a cotangent function, and so it's going to have an amplitude of 2. So when cotangent is equal to 1 or -1 now, we're going to multiply that by 2. So we're going to have to go up 2 and then down 2. And halfway in between here is going to be 2 pi over 4. And then I'm going to go up 2 halfway and then down 2 halfway. It just makes it taller, so I'm connecting the dots here. Now, the period is going to be still between the asymptotes here. So the period is going to be 3 pi over 4 minus pi over 4, which is 2 pi over 4, which is pi over 2. And then the halfway mark here, halfway between pi over 4 and 2 pi over 4. Well, how do we find that? Well, we average. So we're going to say pi over 4 plus 2 pi over 4 times 1/2. That's the same as dividing them by 1/2, or by dividing them by 2. So this is going to be 3 pi over 4 times 1/2, which would be 3 pi over 8. So 3 pi over 8 is going to be this point here. And then maybe you can jump with me and know that this would be 5 pi over 8 because 2 plus 3 is 5. And we would multiply that by 1/2. Hopefully you can see all those numbers. All right. Let's find the domain of this function that we just graphed. The domain is going to be all reals not equal to. Let's pick an asymptote. We'll say pi over 4 plus, how far apart are they? They're pi over 2 apart, so plus pi over 2n, n an element of the integer set. The range here is going to be all real numbers, which is -infinity to infinity. All right. So there you go. There's our first cotangent. And you'll notice that finding the asymptotes allows us to not necessarily worry about starting at the phase shift or anything like we do with sine and cosine. Finding the asymptotes takes care of finding the phase shift, which I think is pretty cool. It's all combined into one step. All right, let's do another tangent graph to make sure we have it. So now I have the tangent of x minus 4 pi over 4. So step 1 is to find the asymptotes. So let's find the asymptotes. All right, to find the asymptotes, what do we have to do? This is a tangent function, so we have to set the angle argument, which is x minus pi over 4, equal to where the tangent is undefined. And the tangent's undefined at -pi over 2 and x minus pi over 4 equal to pi over 2. And then we solve for x. So let's do that. We get x equals negative pi over 2 plus pi over 4. So x equals now negative pi over 2 and fourths is negative 2 pi over 2 plus pi over, I'm sorry, is negative 2 pi over 4 plus pi over 4, which is negative pi over 4. And then on this side, we get x equals pi over 2 plus pi over 4. So this will be 2 pi over 4 plus pi over 4, which is 3 pi over 4. All right, so our asymptotes are going to be, we go to the graph down here, are at negative pi over 4 and at 3 pi over 4. So let's throw our asymptotes in. And what's halfway between pi over 4 and 3 pi over 4? Well, we average the numbers, so it's going to be 3 pi over 4 plus negative pi over 4, which is 2 pi over 4, which is, let's do it down here, negative pi over 4 plus 3 pi over 4, and take half of that. So that's going to be 1/2 times 2 pi over 4, which is going to be just pi over 4. So halfway is pi over 4. So I'm going to put my solid dot here. This is a tangent function with an amplitude of 1. So halfway is going to be 2 pi over 4. That's easy enough to see. And then halfway here is going to be on the y-axis. And so this is a positive tangent function, so it's increasing. So we're going to put our values at 1 with an amplitude of 1 and negative 1. And then we're going to draw our tangent graph. There it is. All right, and let's write the domain down. The domain is going to be all reals not equal to, let's choose an asymptote, negative pi over 4 plus, how far apart of the asymptotes? That's going to be the period, so let's figure that out. I have 3 pi over 4 minus pi over 4 minus a minus pi over 4. So that's going to be, the period here is pi. And that makes sense too, because the b here is 1 and pi over b would be just pi. So this will be plus pi n, an element of the integer set. The range here is going to be all real numbers, just like we've been doing for the ones that were previous. All right, moving right along. Last cotangent function here. Let's graph this one. This is a cotangent, but wait, what's interesting about this one is it's negative here. So we've got to remind ourselves that this is upside down. It's reflected because it is a negative cotangent. But the asymptotes will still be in the same spot. So let's graph that. So find the asymptotes, finding the asymptotes. What do? We set the angle argument, which is x plus pi over 6. X plus pi over 6 equal to where the cotangent is undefined, and that's 0 and x plus pi over 6 equals pi. Now let's solve these for x. We get x equals negative pi over 6 and x equals pi minus pi over 6. And so that would be 6 pi over 6 minus pi over 6 gives us x equals 5 pi over 6. And now we have the asymptotes, so let's put those down. We get pi over 6, negative pi over 6 over here, and then 5 pi over 6. All right, can everybody see that, I hope? And now what I'm going to do is graph, put the asymptotes down. And now I have to figure out what the middle point is. Well, what do we do to figure out the middle point? We just average those two, where the two asymptotes are. So we would say 5 pi over 6 plus negative pi over 6 divided by 2, which is the same as multiplying by 1/2. And so we would say that's equal to 4 pi over 6 times 2, or times 1/2, which means that's going to be 2 pi over 6 is going to be the middle point here. So we'll put 2 pi over 6 right in the middle. And that's the not shifted again up or down, right, because we don't have a vertical shift here. So it's going to be on the midline, which is on the x-axis. All right, so this is a negative cotangent graph. So halfway between, we have to figure out what halfway between is there. So how do I do that? I'm going to average these 2 points. So how do we do that? We go 2 pi over 6 plus 5 pi over 6 is 7 pi over 6 times 1/2 is going to be 7 pi over 12. And then we're going to average these 2 points, which would be 2 pi over 6 plus negative pi over 6 gives us pi over 6 times 1/2, which would be pi over 12. So it's going to be right here, pi over 12. And this is a negative cotangent graph, so it's not decreasing now, it's increasing, which means this is upside down. So we're going to put it at -1 here and 1 in the middle points. And then we're going to connect the dots, and it kind of looks like a tangent graph, doesn't it? It does, because it is reflected over the x-axis, and tangent and cotangents are shifts of each other, just like the sine and the cosine are shifts of each other. And we'll get into that discussion a little bit later. This is just for basic graphing at the moment. So the domain on this one is all real numbers not equal to, let's choose an asymptote of negative pi over 6 plus, how far apart are the asymptotes? Well, that would be the period here, which is from here to here. And to find the period, we just figure out what the distance is. And that's going to be 5 pi over 6 minus a minus pi over 6, which gives us 6 pi over 6. And the period in this one, again, is pi. And so we're going to say plus pi n, an element of the integer set. And the range here is going to be all real numbers. All right. So that's graphing tangent and cotangent. But believe it or not, tangent and cotangent have some cousins called secant and cosecant, and we need to learn how to graph those too. So let's get on with graphing secant and cosecant. Now these might seem a little scary at first, but they're not really, because secant and cosecant, pardon me, are just reciprocal functions of functions we know. And these are the steps to graphing a secant graph. All right, so secant is the reciprocal function of cosine. So what we're going to do is graph the underlying, is what I call it, the underlying cosine guide wave. And that's going to be y equals 4 cosine of x. All right, because this is going to provide us a guide on how to graph this. And this underlying cosine curve is what we've been doing all along. It has an amplitude of 4. It has a period of 2 pi over b. And b in this case is 1, so it's going to be 2 pi. It has an increment, which is the period over 4, which is 2 pi over 4, which is pi over 2. It has a phase shift. Well, wait, oops, it doesn't have a phase shift, so it's 0. It has a midline of y equals 0. And then we have 5 critical points, just like we do graphing all of our sine and cosines from before. And we're going to start at the phase shift of 0. And then we're going to add an increment and go to pi over 2, add another increment, pi, another increment, 3 pi over 2, and then 2 pi. Okay? So let's graph the cosine. So let's do that and label our axes from 0 to 2 pi, and then halfway in the middle is pi, halfway in the middle is pi over 2, halfway in the middle here is 3 pi over 2, and the amplitude is 4, so we're going to have our y-axis up to 4 and down to -4. And in this case, we said the midline was y equals 0, so let's graph our midline, and I'll use orange for our midline today. Here's a midline. Now remember, this is for the underlying cosine graph. Okay, now let's graph the critical points on the cosine just like we would be graphing a cosine curve. That's going to start off the midline and up in amplitude at our phase shift. So it's going to start at 4, then it's going to go to the midline at pi over 2, down in amplitude at pi, back to the midline at 3 pi over 2, and then up back to 4. Now, since this is the underlying guide wave, I'm going to graph this with a dashed line. So this is not actually my function, but it's the guide that's going to get us to graphing the function that we want, which is secant. Okay? Now, the secant function is 1 over cosine. So what happens when x is 0? Well, it's going to be 4 times, and I don't want you guys to do this every time. I'm just going to show you how it works on this first one. If I plug in x and then I figure out what the cosine of x is, and then I figure out what 4 times 1 over cosine x is, because that's the secant, right? So let's go through that process. If I plug in x equals 0, the cosine of 0 is 1. And at 0, I'm going to go 4 times 1 over the cosine of 0, which is 1, so this becomes 4. So my cosecant graph is going to be having a dot right there. It's going to share the high spot there. All right, well, what about at pi over 2? Let's put pi over 2 here. So what's the cosine of pi over 2? Well, the cosine of pi over 2 is 0. So what happens when I go 4 times 1 over the cosine of 0? Pi over 2. That's like saying 4 times 1 over 0. But we can't do that, right? So it's undefined there, which means I have, dun dun dun, a vertical asymptote. Okay? So wherever my function hits the midline, I have a vertical asymptote. So I know that I'm going to have a vertical asymptote then at pi over 2. And where's the cosine 0 again? At 3 pi over 2. So I know I'm going to have a vertical asymptote there. Okay, so last point to try to sell you on this underlying cosine technique. There's a nice point between 0 and pi over 2, which is pi over 3. And I like to use that because the cosine of pi over 3 is 1/2. And so what we're going to do is we're going to plug in 4 times 1 over 1/2, which would be the secant, which is 1 over 1/2, which is going to be 4 times 2, which is 8, which means my secant graph at pi over 3, which is roughly right about here, the secant graph is going to have, instead of 1/2, or 2, in this case maybe, it's going to be up at 8. So what's happening to this graph? Instead of approaching 0, like the cosine does, instead of approaching 0, it's approaching infinity. So this is what the graph's going to look like. It's going to approach the asymptote. So as the cosine is approaching its midline, the secant is approaching its asymptote. It's like we're taking the curve and turning it upside down, reciprocating it. I can't do it in the film like this, but we're taking this curve and we're turning it upside down. We're flipping it upside down, which is almost like reciprocating all the numbers, right? And similarly, down here, we're going to share this point right here, and then we're going to take this curve and flip it upside down. Flip it upside down. Okay? And so that blue curve is the secant curve. And you see how the underlying cosine got us there. All right, well, so let's talk about some properties of the secant, like its domain. We'll put the domain over here. The domain of this curve is going to be all real numbers not equal to, well, where's an asymptote? Well, let's start at pi over 2. Plus, well, when do we get to the next asymptote? Well, it's at 3 pi over 2. So how far apart are they? They're pi apart, so this would be pi n, and an element of the integer set. And the range is a little bit different. The range goes from negative infinity to -4 with a bracket because we have a point at -4. Union bracket, and then it goes, we don't have another y value until we get to 4 to infinity. All right, this function, like sine and cosine, do not have end behavior limits. They have vertical asymptote limits. They don't have any places where they're just increasing or decreasing. They have a, you know, like tangent and cotangent are just increasing or decreasing. What I was trying to say is secant is increasing in this interval, and then it's increasing here, and then it's decreasing, and then it's decreasing again. So there are multiple intervals where it's increasing and decreasing. Now, secant, unlike tangent and cotangent, has a relative minimum here, a relative maximum here, and a relative minimum right here. So this function has some extrema, or local maxes and mins. It is continuous everywhere except where it has a vertical asymptote. This, like tangent and cotangent, is not bounded. The y values aren't bounded. And it's symmetrical with respect to the y-axis, just like cosine is. And so it's even symmetry. And so that's how you graph secant. So let's graph the next one, which would be cosecant. So instead of graphing an underlying cosine function, we're going to graph the underlying, you got it, I heard it out there, ha ha ha. You're going to graph the underlying sine function. So underlying sine function. That's going to be y equals 2 sine of x plus pi over 4 minus 2. So what is the amplitude of this function? Well, it's 2. Its period here is 2 pi over b, and b in this case is 1, so this is 2 pi. The increment is going to be pi over 2. The phase shift here is going to be, the phase shift is going to be negative pi over 4. Sorry. And the midline, I can't spell midi-line, it's midline, is y equals -2. All right, and we're going to have 5 critical points, just like we ordinarily do, starting at our phase shift, which is at negative pi over 4. And then we're adding pi over 2 to it, so that's going to be adding 2 pi over 4. So it'll be negative pi over 4 plus 2 pi over 4 gives us pi over 4, plus another 2 pi over 4, which gives us 3 pi over 4, 5 pi over 4, and then 7 pi over 4. So let's graph our underlying cosine with a -2 midline, and then so I'm going to have to go down all the way to 4. I should make that a little bit more even. -4, this is going to be -2, right? And so my midline is going to be at -2. And my phase shift starts at negative pi over 4, and I'm going to end at 7 pi over 4. Halfway between is going to be about there, 3 pi over 4. Halfway between is going to be at pi over 4. And then halfway between here is 5 pi over 4. And I'm going to use green. This is a sine curve underlying, so we're going to start on the midline at my phase shift, which is going to be at negative pi over 4, start on the midline, and then we're going to go up because it's positive to the next point, and then back to the midline, down to, not very symmetrical, but you get the point, haha. All right, now this is the underlying sine curve, so this is not the actual cosecant graph, so I'm going to graph it dashed. And know that wherever it hits the midline is where my cosecant graph is going to be undefined. So it's hitting the midline at these locations. And then at the high spot, I'm going to take this curve and reciprocate it. There it is, or flip it. And at the low spot, I'm going to take it and reciprocate it. And so the blue curve is my cosecant function. Okay, and so let's talk about its domain. The domain here is going to be all reals not equal to, the first asymptote was at negative pi over 4, plus, the asymptotes are 3 pi over 4, they're pi apart, so this is going to be pi n, an element of the integer set, and the range is going to be from negative infinity till I hit the point right here, so it's going to be negative infinity to negative 4 with a bracket in union with the bracket, and I hit y values again when I get to 0 to infinity. Now I didn't say anything about the period here on cosecant and secant, but the period is going to be the same as the underlying sine or the cosine graph. And a complete period of secant and cosecant is a complete upward U and a complete downward U. Okay, so this one's period is 2 pi, just like the sign beneath it. All right, moving along. Let's do 1/2 secant of x minus pi over 3. So the first thing we're going to do is graph the underlying cosine curve, or wave or function. So that's going to be y equals 1/2 cosine of x minus pi over 3 plus 1. And so this has an amplitude of 1/2. It's got a period of 2 pi over b, and the b in this case is 1, so it's 2 pi. It has an increment of the period over 4, which is 2 pi over 4, which is pi over 2. Has a phase shift of positive pi over 3. Has a midline of y equals 1. And we want 5 critical points for the underlying cosine curve, starting at our phase shift. Now, I have to add pi over 2 to it, so I'm going to change these to a common denominator of 6. So this is going to be 2 pi over 6 for the phase shift and 3 pi over 6 for the increment. And we're going to start at 2 pi over 6, add 3 pi over 6 and get 5 pi over 6, add 3 more and get 8 pi over 6, 3 more and 11 pi over 6, and then 14 pi over 6. And then let's graph our graph, our underlying cosine graph, with a midline at 1. I'm going to show a half here, and this is 1, and then this will be 3/2. And our midline was, we said, I'm going to fold this because it looks better on the screen if it's folded. And we're going to say our midline is at 1. Okay, and we're starting at 2 pi over 6, so we're going to put 2 pi over 6 here. And then we're going to end at 14 pi over 6. Halfway looks right about here, so that'll be 8 pi over 6. And then halfway and then halfway. Let's see here, that's 5 pi over 6 and 11 pi over 6. And this is an underlying cosine curve, so we're going to start up in amplitude at our phase shift, so it's going to be up at 3/2, back to the midline, down to 1/2, back to the midline, up to pi over 6. And since this is a secant curve, I'm going to connect the dots here with a dashed line because the underlying curve is not part of the graph, it's just the guide. And now I graph wherever it hits the midline is where our original function will have asymptotes. And then using blue, I take the high spots here and I take this curve and I flip it upwards. And then down here, I'm going to flip it downwards towards the asymptotes. And then this I'm going to flip upwards. And you'll see that the secant curve has a full downward portion of the graph and an up here that makes a full upward U. All right, so let's discuss what the domain is here. The domain is going to be all reals not equal to, let's choose the asymptote of 5 pi over 6. Plus, how far apart are the asymptotes? 11 pi over 6 minus 5 pi over 6 is 6 pi over 6, so they're pi n apart. And the range is equal to all, not all real numbers, but from negative infinity till we get to the dot here, which is at 1/2, with a bracket, union with bracket 3/2 to infinity. And that's our secant curve. All right, last one. Last one here is cosecant of pi x minus 4 pi. So this is a cosecant graph, so we're going to graph the underlying sine curve or sine wave. And rewriting that, we're going to get y equals sine of, and I'm going to factor out the pi here in the very beginning. So this is going to be pi times x minus 4. All right, and this curve has an amplitude. The amplitude is 1. The period, well, b is changed. B is equal to, let me rewrite that. B is equal to pi. So the period is going to be 2 pi over pi, which is just 2. The increment is going to be the period over 4, which is 2 over 4, or 1/2. The phase shift here is equal to a positive for the midline. I don't have a vertical shift on this one, so it's going to be y equals 0. And then I need some critical points. And then we're going to start at the phase shift, but we're adding 1/2 every time. So I'm going to change 4 into halves, and that's going to be 8 halves, and I'm going to add a half, 9 halves, 10 halves, 11 halves, and 12 halves. And then I'm going to go to my curve up here, and we're starting at 8 halves. And we're ending at 12 halves. The middle is going to be 10 halves and 9 halves and 11 halves. And my midline we said was 0, so I'm going to put my midline on there. There it is. And we're going to say with an amplitude of 1, we're going to go from -1 to 1. This is a sine curve because it's an underlying for a cosecant. So we start on the midline. It's a positive curve, so we're going to go up in amplitude, back to the midline, down in amplitude, back to the midline. And then I'm going to do my underlying curve in dashed lines because it's not part of the curve. It's just the guide wave. And then where my function or my underlying guide wave hits the midline, that's where this cosecant is undefined. So there we go. They're my asymptotes. And then for the fun part, we take the high spot and we take this curve here, and then we flip it upside down. Flip it upside down. And there's one period of our cosecant curve. And so the domain here for our last one is all reals, not equal to. Let's choose an asymptote, and we'll say 8/2, and I can just say that's 4 plus. And then how far apart are the asymptotes? Well, that's 10/2 minus 8/2 is 2/2, so that's just 1 apart. So we can say n an element of the integer set. And then the range is going to be -infinity, because we have y values from -infinity until we get to -1 with a bracket in union with 1 to infinity. And so that is how we graph tangent, cotangent, secant, and cosecant. And I hope you've enjoyed learning how to do so at the Muller kitchen table. Thanks.